Hey everyone, my name is Robert Blanchard and I'm a data scientist at SAS. Today, I'd like to talk to you about auto-tuning deep learning models. Auto-tuning is a technology developed by SAS to intelligently and efficiently search a decision space or set of decision spaces. And a decision space, it's just a theoretical construct of decision-making points that we as data scientists have to make when we develop a model or a code base. For example, let's say that you're doing feature engineering. You may have to choose between bucketing or quantile binning of your interval inputs. On the other hand, if you're building an ensemble of models, let's say gradient boosting or a random forest, you have to make a set of decisions about how you define the base model architecture used in the ensemble. Auto-tuning can help address all of these questions. But today we're going to talk about auto-tuning from the context of deep learning because I'm a deep learning practitioner and that's what I know best. Now, for those of you who uh, work with deep learning, you're probably familiar with two approaches to building a basic model. You're either going to use a backbone model architecture. That's a model architecture built by some other practitioner or used in literature. Or you're going to build a customized model architecture. Regardless of which choice you make, you have to make a set of decisions. For example, if you're using a backbone architecture, you'll have to decide which layers to apply dropout and by how much dropout to apply in each of those corresponding layers. If you're building a customized model, you may be making decisions like, should I use skip layer connections? And where should these connections be in our model? Now, one of the worst or most inefficient approaches to solving these values would be something like a grid search. And I see many practitioners use grid searches to search the decision space. I don't like it because it's highly inefficient and there's not really much intelligence to that search method. Better than a grid search would possibly be a random sample of the decision space. But we're going to go a few steps beyond just a random sample in today's talk. We're going to talk about auto-tuning and highlight three important aspects of auto-tuning. The first most important aspect is the globalized search method. And the second is the localized search method. And the third important point to remember is that SAS Autotuning can evaluate these decision point combinations in parallel. So it's very efficient and very fast. Let's take a look and do a deeper dive into auto-tuning using a few slides, and then we'll jump into the software and run some code. So the first thing that we have to do is we have to sample from the decision space to come up with a set of decision values that we're going to evaluate. We described a simple random sample earlier as one not very intelligent, but usually performs fairly well approach to sampling the decision space. Possibly better than a simple random sample in this context would be something like a Latin hypercube sample. A Latin hypercube sample discretizes the decision space and then searches from various points in this discretized space such that it gets nice uniform coverage of the search space. So in this context, a Latin hypercube sample is best. Now the global method that we're going to detail is a genetic algorithm. So for a genetic algorithm, we first have to sample the decision space. So what sample method should we use? We're going to use a Latin hypercube sample. So we use a Latin hypercube sample and we come up with decision point values. Think of these as learning rate regularizations, dropout, and so forth that we're going to use in our model. So we evaluate these decision point combinations, and let's say we evaluate these points by training our model and looking at performance on some holdout data. So we evaluate these decision point combinations and we identify the best performing evaluations or combinations. We then take those combination values and we separate them into two different groups. The top group that you see on the slide is referred to as crossover, and the bottom group is referred to as pre-next gen. The pre-next gen group, those are just candidates to move forward to the next generation unperturbed or unchanged. The crossover group, those decision point combinations are actually bred together to create offspring For example, if you have two decision point combinations that, let's say, both have three hidden layers as one of their search points that they're looking at, their offspring will have three hidden layers. But let's say that one of the parent decision point combinations has 50 neurons or filters in the first layer, and the other has 30. Their offspring will either have 50 or 30. So we generate a large number of offspring from these parent decision point combinations. We then randomly sample from the offspring, and we randomly sample from the pre-next gen, and take that group and we mutate them. We're going to change the decision space through random mutation. Any of the children not selected for mutation, all of those selected for mutation, and all of those from pre-next gen not selected for mutation become our next generation of decision point combination values that are then evaluated and the process repeats. Now, this is the globalized search method. I don't have a slide to detail the localized search method, so I'll just describe it to you verbally. The localized search method uses a generating set search to greedily search the decision point space. The localized method is parasitic to the global method in that it will perturb or change the best performing model currently discovered from the global method. But they're actually kind of parasitic or feeding into each other because the values, the decision point values resolved from the generating set search method is fed back in to the or used by the genetic algorithm. So it itself can become a parent model or a pre-next gen model. Let's jump into the software and take a look at how to do this in SAS applied to deep learning. So here I am in SAS Studio, and you may notice that SAS Studio looks a little different. Well, I've incorporated dark mode here, which you can do from the options and preferences. So I'm going to begin by creating a local library as well as starting up my CAS libraries. Then I'll load up a few action sets. I'll define a library, load up some images that I'm going to use. So I'll start by running that code. Once finished, I now am going to view the images. Here in the results, we could see that we're trying to classify images that are airplanes versus images that are deer. These are very low resolution images. It comes from the CIFAR 10 data. This is just a toy example to show you the technology. Per good practice, I'm going to shuffle my data. And then after shuffling my data, I'm going to define my model architecture. So in this case, I'm just building a customized model, but I'll show you how to modify a backbone model as well. To build the customized model, I define my model architecture as a type equals CNN for convolutional neural network, and I give it a name. I then proceed to add layers. I begin with an input layer. I then add two convolutional layers, one layer with filters of 1 by 1, and the second layer with filters of 3 by 3. I concatenate this information together, and then I add two pooling layers. Following the pooling layers, I add a convolutional layer with 24 filters, and the filters are of size 3 by 3. I'm going to use a stride value of 2, so I'm downsampling the information. I'm also going to apply batch normalization to this convolutional layer. This convolutional layer with batch normalization, then feeds into the depth-wise separable convolutional layer, which is defined by type equals group convolution. This layer is then fed into the output layer. So let's go ahead and run this code. After defining the model architecture, I can view this model architecture using this fetch action. If you're a traditional SAS programmer, you would just use proc print, and in SAS Via, proc print calls the fetch action underneath the hood.
Aha.
So I'm going to use this fetch action to view the model architecture table. And I'm going to push this model architecture table out to a new window so we can view it real quick. If you're going to use or customize a backbone model, so a model taken from some other practitioner brought in for your data problem, you can modify that architecture using Solve Black Box to come into this table that you see on the screen and change different values. And when you change these values, you change how the model architecture is defined. For example, if we take a look at activation function, we can see that this batch normalization layer is using a rectifier activation function, which has a value of 8. If we want to change this to, let's say, exponential linear unit, I could just come into this model architecture table under this column here and change this value to 10 for exponential linear unit. Here in the code, I've provided just a brief summary of what some of these values mean as or with respect to the activation function. We can then train our model, and we're only going to train our model for 10 epochs. And we're going to use a mini batch size of 10, our learning rate value of 0.01, gamma of 0.6, step size of 3, and then these beta values here. And we're using the beta values from literature. I'm going to train the model and then create an iteration plot that shows the performance of the model. Now remember, SAS makes it easy to use GPUs. I just specified GPU equals true. So it looks as though the model's performance is around 9.5% misclassification rate. Let's see if we can do better using SAS Autotuning. To surface SAS Autotuning, we need to use Solve Black Box. Solve Black Box is an action in the OR action sets. I'm going to begin by loading two tables. These are CSV files. Now, one amazing, awesome thing about Solve Black Box is that you can build upon previous runs. So let's say that before you leave the office tonight, you're going to run Solve Black Box and come in the next morning. You come in the next morning and you notice that Solve Black Box is giving you better results, but it's not exactly as good as you'd like to see your model performing. You could take last night's search values and feed them into tonight's search values to build upon the work that you've already done. I'm going to actually run Solve Black Box now because it's going to need about 400 seconds, 6.5 minutes approximately, to run because we're training, I think, around 45 models. It'll be less than 45. As this runs, I'm going to walk you through this code so that you can do this yourself from your office or home. So I'm loading up these two CSV files. We'll come back to these later, what they mean or what they're being used for. I begin with an initialization source code. So in this initialization source code, Solve Black Box runs this once. And this is where you would typically load your action sets, define your libraries, load your data, prepare your data, and so forth. So Solve Black Box will loop through this code block once. Notice I have an end source which defines the end of this code block here. Next, I create a new source, which is the evaluation code block. I can name this whatever I'd like to name this evaluation code block. Just like the initialization code block, this has an end source to end the evaluation code block. In this evaluation code block, SAS is going to find the decision variable names, which you define as the user, and it's going to change those decision variable names to values from the search space that you've set up. So notice This code right here is building the same model architecture as we saw above, with the exception that we have decision values planted in the code. We're looking at the filter width and height for both the convolutional layer as well as the group convolution layer. Next, we're going to use this set of code here to update the model architecture table, changing the various activation functions. Following that code, we've finished modifying the architecture. We then train the model using DL-train. In DL-train, we have two decision values that we've set. We're going to search beta 1 and beta 2. Now, most of us always use what the authors of Atom recommend. For beta 2, I think it's 0.999, and for beta 1, it's either 0.9 or 0.99. And in fact, in our base model, that's what we used. But here, we're going to use Solve Black Box to actually search these values. After we train the model, we're then going to score the training data. And notice after DL score, we've got this result equals S. We're going to take all of the output tables from DL score and save them in an object S that we can then reference to pull out the misclassification rate. So I know that included in the output tables by DL score is a score info table. And in that table, there's a value, there's a column called value, and the third value down is the misclassification rate. I know that from experience. All you have to do is look at the table and the name of the table in the output. So we create this error value, which is just the misclassification rate from our training data. We save that value in a function variable called objval, and we're going to send that response out to Solve Black Box. So at the end source, you can think of this as a giant do loop where SAS is changing those decision point values. In the Solve Black Box action, we may want to first specify our decision variables. And in the decision variables, you just specify the decision variable names. You define those names. Type equals is where you specify whether the decision variable that you're searching is either an integer, contains integer values, or continuous values. And then you set the lower bound and upper bound of that search space. So notice for the kernel sizes, or our filter sizes, we're searching between 1 and 5 for the kernel size. So we could have a width of maybe 2 and a height of 5 or something of that nature, a width of 1 and a height of 3 and so forth. Oh, I should have said width here and height here. Then for the activation function types, we're searching between 8 and 10. And if we go up to our little reference, 8 is ReLU and 10 is ELU. So we're going to have soft plus as well in there. So we're going to search ReLU, soft plus, and exponential linear unit. Looks like Solve Black Box is finished. In addition to the activation functions, we're going to search two hyperparameter values, our betas for Atom. In the obj equals option, we specify the name of the objective function and whether we want to minimize or maximize it. In the cache-in table, we can specify. So the cache-in table as well as the first gen table, these two options are optional in that the cache-in table tells SAS, I've already sampled these decision points. In fact, prior to running this program here, I actually ran Solve Black Box and sampled from about 255 different decision points in the decision space. So from those 255, I sorted the data from best performing to worst performing, and I took the top 8 observations. Those top 8 observations were fed in as the best input. So for this run right here, in this first gen equals, we're providing Solve Black Box with the top 8 performing combinations from the last search that we did before this video. In the cache in, we're specifying all of the other decision points less the decision point combinations from best input. And this tells Solve Black Box and SAS, don't sample from these values. We've already sampled them. Don't waste your time. Search elsewhere. In the cache out equals, we specify the name of the data set that we'd like to create, which is going to contain all of the decision point combination values and the corresponding objective function. If you notice over here in the results window, it's this table right here that I'm highlighting. Remember, Solve Black Box can actually run in parallel, and if you're doing deep learning, it's likely you're using GPUs. You'll just want to make sure that you have multiple GPUs on your system if you're going to run your model or train your model in parallel, or evaluate those decision point combinations in parallel. Population size is the initial sample size, or the sample of decision point combinations for each population. The max gen is the number of generations that we're going to loop through as we search the decision space. The end local specifies whether or not you want to use the generating set search, that greedy localized search method. If you set end local to 1, the GSS will effectively take a step in a different direction in the decision space, but only one step. For example, think of a two-dimensional space. The GSS will step north, it'll step west, it'll step south, and it'll step east. If you change end local to 2, then the GSS will take 2 steps. It'll step north and west, and then south and east. This option here, nabs f conv, this is where you can specify some convergence criteria. Notice I've set it to some ridiculously high number. I've done that because I would rather the algorithm stop when max time is reached or when the population, the max number of population is reached. And that's population multiplied by generation. We have our seed, and then notice that this cache out table here is being fed into the equivalent of proc print, or the fetch action, to print the results sorted by the objective function value in ascending order. And then I'm going to save this out into a CSV. I'm doing this in case I want to again do another search. Maybe the performance that we see here is not good enough. Now notice the objective function value is now 5%. So we have a 5% misclassification rate, as opposed to earlier we saw about a 9.5%. So using Solve Black Box, we've been able to improve the model's fit to this data. And as you're probably familiar, being a deep learning practitioner, you're going to want to use Solve Black Box to find a good model architecture or to customize a backbone to better fit your data, and then leverage Solve Black Box to get a model that generalizes well. Search what layer you should apply dropout and how much dropout you should apply, and search those regularizations as well. So I hope you enjoyed today's video on auto-tuning deep learning models. Don't forget to check out the links below, add in any comments or questions that you may have, and definitely subscribe to SAS users to see more content like this. Take care, and I'll see you next time.